So this is example 20 in the vectors topic. We looked in example 19 at finding the point of intersection of two lines. What I want to do in this example here is look at the point of intersection between a line and a plane. So this is a slightly different situation. In the previous one, we looked at changing the equation of a line from symmetric or Cartesian form into parametric form, because when we're looking at points of intersection, we're looking at algebraically putting two equations together, and the best way to represent a line when we're doing that is in parametric form. So we're still going to do that here. We're going to have one line in parametric form, and we're going to have this time a plane. And if we can see the difference in the equation of the plane, you can notice that what we're really going to do in the end, our goal, is to find in parametric form our equations for x, y, and z, and we're just going to substitute those equations into the equation of the plane. It's similar probably from previous experience when you had the equation of a line, for instance, and you had the equation of a circle. You might have come across the idea of finding the intersection in 2 dimensions of a circle and a line, and the circle might look like something like that. And what we do is substitute this expression 2x plus 1 into our expression for y, and what that did was we had then reduced that to an equation in one variable. Now we would say at the point of intersection only, then the y coordinates are the same, and if that y coordinate is the same as that y coordinate, then we can say that 2x plus 1 is going to be the same as y just for the point of intersection. So we're hopefully familiar with the idea of finding a point of intersection of a linear function and something that's a wee bit more complex, and that's exactly what we're going to do here. The only problem is we're actually missing the equation of the line, and we're going to have to work for it in this particular situation. So I'm told that there's a plane. I'm going to represent that by my parallelogram. It's my kind of 3-dimensional plane with a bit of perspective. And we're told here we've got a plane with an equation. Yep, so we're good for that. But the line is actually perpendicular to this plane. So we've got a perpendicular line. We know that it's at right angles to the plane, and the line passes through the point A, which is 353. So the first thing we need to do is to come up with the equation of our line. Well, what do we need for the equation of a line? We need a direction vector and a point. We already have a point. So we know that we can write the equation of the line in this form here, symmetric form. We have a point. Remember, it's all y minus z, with x minus, y minus, z minus, and look at our 3 points, 3, 5, 3, they're all positive, which means we don't have to make any of the minus signs. Plus 3, 5, 3, so we've got half of the equation of our line. The direction vector of the line we don't know. Well, a little leap of deduction, I'm sure you're screaming that already. Well, if we know that the line is perpendicular to the plane, we also know something else about a vector that's perpendicular to the plane, and that is the normal vector of the plane. So as L is perpendicular to the plane, we can say the direction vector of the line is equal to the normal vector of the plane. So we're saying here that the direction vector of the line is going to be the same as the normal vector of the plane. So we can just basically nick the direction vector, the normal vector of the plane, which is 2, 3, and 5, and there we've got the equation of our line. wee bit of vector deduction there. So now we've got the equation of the line. It's not in a good form to actually use any substitution. What we want to do is to change it into parametric form. So I'm going to remember and introduce a parameter that we can always write at the end of those equations. Allow me to then rewrite them in parametric form. So I can take the x term here, x minus 3 equals, and then if you multiply both sides by 2, you get equals 2t. Hopefully you're familiar with changing from symmetric to parametric form. If not, go back and study it, because I'm not explaining it here. So we've got our three equations, parametric equations, which is the same form of the line. Okay, so we've got our three expressions for x, y, and z in terms of t. So all we need to do now is to state that for the point of intersection, something magical happens. We know that, of course, the x, y, and z coordinates on the parametric form of the line have to equal the x, y, and z coordinates on the plane. Therefore, if we start with the equation of our plane, 2x plus 3y plus 5z equals negative 2, then just like I was demonstrating with the equation of the circle, we can say that we can substitute in our expressions for x, y, and z in terms of t for the line. So here's the line going into the plane, and at the point where they meet, we're going to get a value for t. Okay, so it's just a case then of multiplying out carefully. 40 and 90, 25t is 38t. 6 and 15, 21 plus 15 is 36. It's negative 2. 38t equals negative 38. A bit more space on that, so t is equal to negative 1. So at the point of intersection, t is negative 1. That's not the actual coordinates of the point of intersection. So it's a simple matter of taking the three parametric equations. We've got x equals 2t plus 3, which means that our x coordinate is going to be 2 times negative 1 plus 3, which is 1. Our y version is up at the top there, 3t plus 5. So that's going to be 3 times negative 1 plus 5, which is 2. Z is 5t plus 3 equals 5t plus 3. It's negative 5 plus 3 is negative 2. And therefore, we can say, with a great flourish, the point of intersection of the line and the plane is 1, 2, negative 2. Okay, so some of our work there was actually finding the equation of the line. But once you do have the equation of the line and the plane, then it's simply just a matter of substituting the parametric form into the equation of the plane, finding t, and then evaluating the x, y, and z coordinates. Okay, it's a nice problem to solve, but as always, sometimes you have to work to actually get to the point of substitution. Okay, that's how we find the point of intersection of a line and a plane. We're going to go on and have a look at how we find the investigating the intersection of planes, 2 planes intersecting or 3 planes intersecting. So keep watching the different examples, and hopefully that will help your knowledge of all this intersection business.